like something like that. There's hardly any intensity because you have simply diluted the molecule. Okay. So the only way if you want to get more of that is take a long path length cell because real Lambert law says absorbance equals epsilon, the concentration is the length. Epsilon, you can't touch it, it's not given. Concentration, yes, you can play with it, but here I deliberately reduce my concentration. So what's the only thing left for me? Length. So then you should come back to me and say, can I have a cell of this bigger length? And then you fill this up, it's a large length. I mean, don't laugh, there are cells which are like 1 meter long. And you can do experiments. In fact, you're dealing with spectral features of extremely weak intensities. Then you actually have to take a cell which is like 1 meter long, fill it up, and then do your experiment with that. And then you can do something very interesting. And what is that? You take the cell, fill your gas here, the gas fills up, this length is 1 meter, or much, quite long. It's not enough. I want something like 100 meters. So obviously you can't get a cell like 100 meters and put it into your machine. So what you do is you silver this slightly, you silver this slightly. So what happens to the light that gets in? When it gets in, it's like so it gets out. So it's making multiple passes and you get 100 meters that way. So you can play all these sort of games. But of course, optics comes in. You have to get your physics straight out here. You want to do these experiments. The point therefore is, the computation is very small like that. These are the experiments. Coming back to what we were looking at, line. So if you have features that are extremely diluted, not interacting with each other, then you can actually kill collision, you can actually kill interactions and sharpen your features. Comes back to the same point I made earlier. If you want to sharpen your features, you must know who's making it broad in the first place. And if you knew that, then of course you can play all these games. Most of the time it's Doppler, it's collisional, it's interaction, it's time of flight, or what have you. You just have to figure out who's doing the broadening. And there are some very elegant and very unambiguous experimental methods by which you can actually figure out who's doing it. So that's basically what I want you to know about line broadening, because you can't go through a course on spectroscopy and not even have heard about lines being broad and for what reasons they are broad. That's why, even though Banwell has not really discussed it, I just thought I should let you know. But all I'm expecting you to know in this is whatever I said here, and all I'm expecting you to know is how to operate these and decide under conditions of the experiment which is broad. Now you can actually see that you can actually use this Doppler width to get the temperature of the system. If you knew what the Doppler width was, if you measured it, and if you are convinced that that width is due to Doppler, you have to know that, as I said, and you must know who is broadening you in the first place. So if you knew that Doppler is the one that is broadening it, measure the width, full width half max. You know everything else, go back and measure temperature. This is another way by which you can get temperature. Sticking a mercury thermometer into your sample is not the only way by which you can get temperature. In fact, that's probably the least used of all ways in very many experiments. You will use rotational line distribution, vibration line distribution, drift of the curves, blackbody radiation, all sorts of issues to get the temperature. This is one way by which you can do it. Okay? Actually, I want to spend maybe this class and one more class on electronic spectroscopy and then move on to NMR after that. So, what I want to introduce you to at this point is a new technique in spectroscopy called photoelectron spectroscopy. Actually, with light, there's a whole lot of things you can do. You can do photochemistry, you know that. Shine light, bake the molecule, do chemistry on it, photochemistry. You can do photoelectron spectroscopy, meaning I shine light, I I remove the electron, ionic carbon. I report the electron process. And right at this very minute, there's probably a seminar going which I came out where you are doing photoelectrochemistry. You can put two electrodes into a solution and get current out of it, right? You know that. The Nernst equation and all these things. But then what I can do is I can put two electrodes inside, I don't get a current, I shine light on it, I start getting a current. So I'm basically doing photoelectrochemistry, and this is being started off as being a good method by which I can harvest light energy. So as the light falls on it, I actually produce an EMF and therefore a current in the external circuit. So this can be coupled with a whole lot of things like electrochemistry or simple chemistry, or you can do photothermal properties that you shine light and convert it to heat, and therefore you will find that there's a whole lot of things that you can do by simply letting the molecule absorb light. What we will do today is look at the process of photoelectron spectroscopy. I shine light, I take an electron out, I produce a positive ion. So I have N plus is mu and plus. So I can basically take a molecule in its ground electronic state, and I can do so many of these curves from here. But what did we assume when we do all these curves? We assume we are changing the electronic configuration. We are taking the electron from one orbital, putting it in another orbital. But at no point did I ever say to take the electron and snatch it away. I didn't do that. So I'm transferring the electron from one orbital to another orbital and looking at transitions between these orbitals, and that's basically what we were doing. Now we're going to the limit. You take the electron, put it to the next orbital, or the next one, the next one. Finally, the electron keeps going further and further out. It's now no longer under the control of the nucleus, boom, it's gone. And now we have a positive ion. And therefore, I produced a positive ion by simply shining light on it. We can produce positive ions in a variety of ways. I can take the molecule, put two electrodes, and strike a potential, few kilovolts. I strike a discharge, and these electrons that go from one electrode to the other under the potential difference of 1, 2 kilovolts or whatever, will actually have enough energy in them that when they collide with the molecule, they will quickly knock off one electron on the way and go away. In other words, I am using an electric discharge to produce ions. I can do that. So every time you have electric discharge between two leaky points or badly connected points, mind you, I am producing ions right there. Every time there is an electric discharge in the atmosphere, there are ions being produced at that point in time. We produce ions simply by striking the electric discharge. That's one way to do it. The other way to do it is simply take the molecules, shine light on it, and simply excite the electron from one of the orbitals, let's say the ground electronic configuration, and simply use it to be pushed up to such a point that it is no longer under the control of the nucleus, and therefore it is free to go. And when it is free to go, you basically have this reaction happening, and you have a plus plus E minus. This is this very celebrated photoelectric effect. So if I have a molecule up here whose energy is N, and here is the energy of the ion in plus, what do you call this energy as? Ionization potential or ionization energy, and if it's a solid, we call it as work function. For an isolated molecule, we call that as the ionization potential. That's the minimum energy required to remove an electron from the molecule. And I'm very sure you have been studying organic, simply bored you to death by saying that as you go down the group, the ionization potential decreases and so on and so forth. Of course, not in all cases, you have exceptions to that. But then the point is that as you keep going down the group, the outermost electron is so far away from the nucleus that it doesn't take you a whole lot to get it out. And therefore, the ionization potential actually decreases. But the point is that energy that is required, take a molecule or an atom and feed the electron away. But then, if I take this much energy, what happens? Now let's look at atoms. Let's not get into molecules. Because once you get into molecules, you have all these people who will be bothering us, the Franks, the Collins, and so on. So we will not worry about molecules at this point. We look at atoms. I take an atom, I go here, I produce the ion. Let's say argon. What's the electronic configuration for argon? 1s2, 2s2, 2p6, 3s2, 3p6. Okay, it's a 3p6, p6 configuration. So the outermost orbital in argon has to be p6. So when I shine light, who's the first one who's going to put up its hand to leave? The p electron, not the s electron. The s electron is sitting buried inside and sort of reluctant to leave. You have to give a lot more energy to kick this guy. The one that is very ready to leave, now the most ready to leave, is going to be the outermost orbital, the extremely peripheral located valence electron, which is the p6. So what is the electronic configuration here? p5. The one electron has already gone out. And this is going to be the energy that is required to remove the electron from argon, and therefore it's the ionization potential of argon. If I gave this energy, I have just barely caused ionization. But if I gave this much energy, I have caused more than ionization. I have given extra energy. And who takes this extra energy away? The electron. And they will take it away as there's nothing else the electron can do. It has to take it away as kinetic energy. Therefore, all the energy that is required to cause this jump or cause the ionization is eaten away. And whatever balance there is given to the electron, and which takes away as your kinetic energy. And therefore, we have this celebrated photoelectric equation which says that the energy of the photon minus the ionization potential must be equal to the kinetic energy of the electron. It looks very simple, but quite a powerful equation. Why is it powerful? Because if I ever have to find out what the ionization potential is for a molecule, how do I get that? If I know what light I'm using, I know the frequency of light I'm using, it is very easy to find out. All you have to do is to set the light to a monochromatic, set your basing, and you get that frequency. I'm very sure you have used that in your UV visible spectrometer. As the grating moves, you're getting one wavelength after another. So you can set your grating to give you, let us say, 350 nanometers, and what comes out of the monochromator or the spectrometer will be 350 nanometers. Therefore, I can pick my wavelength of choice. Let's say I pick this. I don't know this. I'm trying to figure out what the ionization potential is. What can I do? I can measure the kinetic energy of the electron as it comes out. As the electron comes out, I just measure what the kinetic energy is, and if I know the kinetic energy, then of course I have an accurate estimate of the ionization potential of the material. Extremely important information. The photoelectric effect actually gives you a method to very accurately determine this quantity. Question of course is, how do I experimentally determine the kinetic energy of the electron? There are many ways. I just tell you one way, which is pretty straightforward and very simple. So I measure this, I know this, I get this, which is very important. It actually tells me something about the molecule. It's a molecular property or an atomic property, which very often I'm looking for. So depending on what energy you have, you will get a greater or a lower kinetic energy. If I use the photon energy, which is just threshold, then what happens? The electron barely moves out and has about infinitesimally small kinetic energy. But whatever it is, I can use it. How can I measure the kinetic energy? How would you measure the kinetic energy of a stone if I ask you to do it? You just choose something and ask you to measure the kinetic energy of a stone. How would you do it? How do you measure the kinetic energy of a physical dipole? How do you do that? Today we keep showing you all that. 140 kilometers per hour, 130 kilometers per hour. Which of course once you know that, you know the kinetic energy of the ball as it's traveling. So what are they really doing? Just high-speed cameras, and they get to know the position of the ball at two different points, and they know the time. Therefore, they know the velocity. It's simple. So do the same thing. It's almost like getting one of these high-speed cameras from 10 ports or ESPN and finding out what the kinetic energy of the electron is. You just do it slightly differently. What you do is the following. I have a detector onto which if an electron hits, it produces a current flow. Where at the end of the day, electron is negatively charged. So if I hit a negative charge species, the current is produced and I can actually measure the current. So every time an electron hits this, I would get a current. I have to measure that. How big the current is not the point. The point is if an electron hits it or when an electron hits it, I can actually record that image as a small spike in my current to that circuit. What I do is I have the molecules, let's say a baton that's going by. I come in with light in this direction and I focus it right here such that the frequency is whatever I think it should be. At some frequency nu, I focus the light beam out here, excepting that I will use this light beam in pulses, extremely sharp pulses, like 10 nanoseconds. So light go on for 10 nanoseconds, it's off. 10 nanoseconds, it's off. So when this light comes in and it is on for 10 nanoseconds, what does it do during those 10 nanoseconds? It ionizes the molecules because it is there. The molecule will absorb the light, and if that light energy is greater than the ionization potential, ionization is caused. Moving ionization is caused, what happens to the electrons? Oh, they will start move. So what I do is, the moment the light reaches here and hits that point, I start a clock, an electronic clock. And the clock keeps ticking. The moment the electron reaches here, a current is produced, and I now make this signal go back and stop the clock. And this can be very easily done in electronics. You have a start pulse and you have a stop pulse. So I can take this start pulse for my timer, and I can give this as my stop pulse for the timer. And all